Welcome back, everyone. In this video, I will begin going over the lecture for the graphs and derivatives section. Now, as far as this section goes, we have talked about the graphs and the first derivative quite a bit. And just as a quick review, we know that if the first derivative is positive, then the graph is increasing. And if the if the first derivative is negative, then the graph is decreasing. And a couple of sections ago, we talked a little bit about the derivative equaling 0. We know those points. It's not all the possible critical numbers, but this will give you some of the critical numbers. But really what we established is that those critical numbers, we saw examples where we had a local maximum, a local minimum, or neither. Now in this section, and pretty much any of the sections going forward, we're mainly going to focus on the derivative equaling 0. And the reason for that is those are the kind of functions when the derivative equals 0, they typically model some real life situations. If you have the derivative does not exist, that can certainly happen, but it doesn't happen nearly as often. So think of the derivative equaling 0 as your critical values, even though, like I just mentioned, there could be more. But we pretty much know everything about the first derivative. We can look at a graph and know whether it's positive or negative. You can't really go much beyond that. We can't say if it's 2 or 3 or whatever, because it's pretty hard to do that without computing the derivative. But what we really want to do in this section is add in what the second derivative means visually, some idea called concavity, and kind of bring it together with the first derivative. And then at the end of the section, really what we want to do is, given a formula, we want to find everything about the function. We want to know where it's increasing, decreasing, where our local extrema are. We also want to know where it's going to be concave up and down, which is related to the second derivative. And a similar idea to the local extrema would be the inflection points for the second derivative. All right, so that's just a little preview. Now, for the most part, at the beginning of this section, we're just talking about graphs and really looking at graphs and relating them. And this first little bit here, I have the one on the left here is the graph of y equals x. That's just a line. The one in the middle is the graph of y equals x squared, which is the parabola opening upward. And the one on the right is y equals negative x squared, which is the parabola opening down. Now, the reason I bring this up is I want you to understand a little bit about what concavity means. So concavity is related to the second derivative. And pretty much just like the first derivative is related to increasing and decreasing, it's not necessarily the number that's super important when we're looking at a graph. It's whether it's positive, negative, or 0. And I went ahead and just computed the first and second derivatives pretty quickly for you. We want to really just focus on the second derivative here. And what you'll notice about the second derivative of y equals x, it is 0. Now, what concavity really does is it represents the bend of a graph, right? So think about what you might think of by bending. It's not a straight line. So when the second derivative is 0 like this, that means your graph is actually a straight line and there's no bend at all. So let's go ahead and write that down. The second derivative equals 0 means it's not bending. Now, this is an example of a graph where the second derivative is 0 everywhere, which means it's not bending everywhere. Sort of like when you can have the first derivative equaling 0, have a local maximum or minimum, you can just have the second derivative equaling 0 at spots, and those will be called these things called inflection points. But we'll get to that in a little bit. So the idea here is just to understand that the second derivative is representing bending. When it equals 0, there's not bending. Now the middle one here, the graph of y equals x squared, the derivative formula is just 2. That means it's always 2 no matter what x is. But the main thing you want to notice here is that for this graph, it's bending up. And the best way to think about concavity is imagine using your hand and trying to wrap it around this, just make this shape. Your hand naturally has to bend up. Okay, your palm is pointing up to the sky, maybe a good way to think about it. But this thing is bending up, and that's really what the second derivative being positive means. So second derivative greater than 0, it means it's bending up. And for the purposes of what we're going to be talking about with concavity, this can be represented also by being concave up. So when the second derivative is positive, it means visually it's bending up. And the way we're going to word that is it's concave up. And now for the second derivative of y equals negative x squared, you can see this graph is bending down. Once again, think about wrapping your hand in this downward U shape. Your palm is going to face downward. And the second derivative is negative here. It's -2. It's always -2. So what this is really telling you and what you want to have in your head is that when the second derivative is less than 0 or negative, this means it's bending down. All right, so visually it's bending down. And what we really want to go after here is that the word we're going to use is it's concave down. I actually just noticed that this gets a little cut off when it's recording, so you might not be able to see it. Let me go ahead and just rewrite this. This is just the second derivative is less than 0. That's still not in range. My apologies. It's on my screen, but now I can see from where it's recording, it's not actually on the recorded part. So the second derivative less than 0 means it's bending down, and the second derivative is just equal to -2. So that's just a -2 there. But you can compute that yourself. The derivative of -2x is just -2. All right, so the idea of concavity is this bend thing. If it's 0, it's not bending. If it's positive, it's bending up. And if it's negative, it's bending down. That quantity doesn't matter. So whether it's 2 or 100, it's bending up. The bigger the number is, or actually the farther away from 0 it is the more it bends that way. So if you have a function that's second derivative is 100, then it's going to be bended up really sharply. It would probably look something like this, although I'll erase that to avoid any confusion, but it would bend more sharply. But just really like with the first derivative and increasing and decreasing, if we're looking at a graph, we can't really know whether it's the second derivative is 2 or 1. It could be 0.01. It could be 1,000. It's really just whether it's positive. All right. So one thing I think is really useful is that when the first and second derivatives interact, the pictures can be really thought of as these 4 things. So I have a little chart here, and I have f prime is greater than 0. That's going to be this row. So our graphs will be increasing. But I want to look at what does it look like when it's concave up, and what does it look like when it's concave down. Well, you can actually look at these 2 pictures and actually get that. So if you're looking at this graph, the graph of the parabola, that's where the second derivative is positive. So it's concave up. So we're in this column. And when it's increasing, it's this part. So anytime you have an increasing concave up graph, it's going to look something like this. It's bending up, which is the concave up part. The second derivative is greater than 0. And it's increasing, which is the first derivative being positive. Now, if we want to look at increasing, but for concave down, this is the picture we want to have in our head for concave down. And when it's increasing, this graph, it's on the left half here. So this is going up, but it's bending down as it goes up. So it looks something like this. Right, so it's increasing, it's going up. You should hopefully be very comfortable with what that's saying. It's going up. However, it's definitely bending down, because if we try to wrap our hand around this, like imagine putting your hand in this shape, your palm's gonna have to face down. It's not gonna face up. So this is this picture you kind of want to have in your head when you're looking at an increasing but concave down. So it's bending down, but it's still increasing. Let me actually just spell out increasing for simplicity. And now when you look at decreasing, you can really look at the same graphs and just the other side. So concave up is the upward parabola, but if it's decreasing, we would be on the left side here, because as we move to the right, it's going down. So it looks something like this. And once again, you can see you can probably more comfortable with the increasing and decreasing part. But the reason this is bending up is, once again, imagine wrapping your hand in this shape, making your hand with this shape, your palm will be facing upward. So this is bending up, which means concave up, and it's decreasing because it's moving down. And then decreasing and concave down would be the right half of the downward parabola. It's going down and it's also bending down. So it looks something like this. And the point is, any graph will be broken down into pieces like this. It'll be either be bending up, bending down, concave up, or concave down. So it has to fall on one of these 4 pictures. Of course, you can have a bunch of these attached together. But let me go ahead and write that down. So this one is bending down because if we wrap our hand around it, our palm's going to be facing downward. And it's decreasing because as we move to the right, it's going down. So one kind of thing to add in right here is that because the second derivative gives you concavity, when you compare it to the original function, it gives you this bending action. One thing it could be worded is not necessarily concavity, but because the second derivative is the first derivative of the derivative, because when we do the derivative of f prime, that's when we get f prime prime, it tells you the rate of change of the derivative. So we can kind of interpret concavity as this. If we're concave up, what we're saying is the first derivative is increasing. And maybe you have to take a moment here, but remember the first derivative is just a function. Now, whether it's positive or negative will tell you what the original function is doing. But since concavity is the second derivative, it'll tell you how the first derivative is changing, whether it's increasing or decreasing. And you'll very often see in word problems like this, we won't necessarily use the word concavity, we'll more so use the word how the first derivative is changing. Concave up means the first derivative is increasing. Now that's just because if we start with f prime and we do its derivative, well, if it's positive, that means the thing we're doing the derivative of, which is f prime, I didn't mean for that straight mark, f prime is increasing. So concave up is f prime prime, which is this, but it's really just doing the first derivative of the derivative, and that means increasing. And then concave down is pretty much the same way. How is it telling you the first derivative is changing? Well, because it's negative, the second derivative would be negative. This is telling you that the first derivative is decreasing. And same idea here. If you do take the first derivative and you do its derivative and it's negative, that means that f prime is decreasing. Right, and you can kind of get it from these pictures as well. So let's just look at this one here. The f prime is 0, or sorry, positive, so it's going up. But as it's bending upward, that means the slope is getting more steep. Imagine if this was the path a ball was taking or something. Well, then what is happening here is it's saying, at this point, it's barely moving up, but then it starts moving up faster and faster and faster, and it's just increasing faster and faster. That's exactly what the bending up says, is that our derivative, maybe it starts off at 0.1, then it's 0.2, then it gets to 1, 2, 4, and it just becomes more and more steep in a positive way. So the first derivative is increasing. But if we look at the increasing version, but when the graph is concave, you can see that it's slowing down. So imagine once again, your ball is increasing, but eventually it starts slowing down. That's exactly what's happening here. So maybe the speed of it is 5, 5, 4, 3, 2, 1. Because it's not going up as fast, the speed is slowing down. And eventually it basically gets really close to 0 because it's almost a flat picture. Now, when we talk about word problems, like I said, we'll pretty much use this idea for what the second derivative means. When we talk about the graph specifically, we usually use the word concavity. So just be aware of that. right? But what I want to do here is go ahead and just do one problem in this video related to all this stuff. And the emphasis of this course and pretty much everything we do is to understand what's happening graphically, but be able to do it with formulas or do it analytically. So we'll just go ahead and start by doing one graphically to really understand what's going on. And then what we'll do after this problem is really just work with formulas. All right, so this is the graph of y equals f of x. And I'll go ahead and scroll down real quickly, but basically from this graph, we want to answer everything. We want to know where the function is increasing, the function is decreasing, the function is concave up, the function is concave down, the local extrema, so maximums and minimums. Remember, that's going to be local, so the endpoints aren't important as far as local goes. And then the other thing we want is the coordinates of the points of inflection. Now, when we get down here, I haven't formally defined it yet, but I'll go ahead and make sure we define it when we talk about it in this problem. All right. Now, one thing I want to go ahead and mention is that for these first four things, when you're talking about the intervals where a function is increasing, decreasing, concave up, or concave down, you're wanting intervals of x. So you're not going to care about the y value when you talk about where something is increasing, decreasing, concave up, or concave down. You just want intervals of x. Well, let's do increasing first. All right, so increasing is just our old one. It's as we move to the right, when are we going up? We're going up, 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 and we're going up. We're still going up, even though it's flattening out, we're going up until we get to that point. So it's increasing there. Then we're going to go down for a while, so that's decreasing, but I'm just going to mark off the increasing first, decreasing until we get to 4 here, and then it starts going up again. Now, it's still going up. It's sort of flattening out. It might become completely flat, but because it continues back increasing, we actually just let this whole spot represent increasing. And that's something that might be a little weird, is because it's flattening out, maybe it's not actually increasing for just a very brief moment. But if it's just increasing and then it flattens out and then it starts increasing again like that, we just consider it to be increasing the whole time. Well, what are the intervals here? One thing is that the homework and the problems in general really give you a big hint of open intervals, because whenever you're increasing, decreasing, or talking about concavity, you never include endpoints. So it's always an interval that's open, which means parentheses on both sides. The first one is starting at x equals 0 and going to x equals 2. And we do have another interval, so either use a union or you can just use a comma to separate them. And then the other x values where it's increasing, it starts increasing at 4 again until we get to 5. Right? But don't let the fact that there's endpoints with filled in circles bother you. These must be open intervals. So it has to be a parentheses on 0, even though there's a closed circle. It has to be a parentheses on 5, even though there's a closed circle. All right, now where is it decreasing? Well, we kind of did that as we went through it, but it's just decreasing where it's going down as we go to the right. So from 2 to 4, x equals 2 to x equals 4. And there's only one interval where it's decreasing, so that's it. All right, now the concavity, let me go ahead and erase that. The concavity can be a little tricky, especially at first, because concavity means bending. So concave up is where it's bending up. And the best thing you can think about is either having these pictures in your head. So these two are where it's bending up. You can think about it as being each half of the parabola. So if you kind of attach these together, you would get the parabola going upward. Or you can think about, just sort of, if I tried to trace this with my hand, make shapes with my hand as I went on, where is it bending up? Well, if you start here, it's actually bending up right away. It's bending up until we get to some point around right here, because then it starts slowing down. It's bending down. So it's really only bending up for the first little section here. And once again, whether you have this picture in your head or try to trace it along with your hand, if you try, try to make that shape with your hand. I apologize if that was loud. I just smacked my microphone by accident. If you try to make this shape with your hand, eventually you're not going to be able to make the shape all the way up here, because then, you know, kind of what's going to happen is you're going to be bending up, but then your fingers would have to start bending down, which is going to be impossible to shape your hand that way unless if you're, you know, you're double jointed or something like that. And really, we just try to best estimate where we think it starts bending down. It's definitely bending down here. So at this little portion, so it's just probably somewhere around here. And my best piece of advice is, you know, it's probably going to start bending down at a whole number, because we can't really see if it would be like 0.7 or 0.8 or 0.9 or 1.1. So I'm going to start with 0 to 1. Now we might have more places where it's concave up, but because this is concavity and we haven't dealt with it, I'm just going to go left to right. So at this point, it starts bending down, right? Like we discussed, it's still bending down even when we're at the top. So you could make the top shape by the entire top shape, sort of like the upside down U here, with your whole hand bending down. So it's still bending down, still bending down, still bending down, still bending down, and it's bending down really until we get to some point around right here. Once again, it's really impossible to say exactly where it stops bending down just visually. However, if you look over here, it's definitely got to be bending up. And imagine making the shape with your hand. It's going to be bending up around here. So I just use my best guess and say, you know, it's around 3 is where it stops bending down. So this is concave down. And that's the interval from 1 to 3 with X. Now we might have more, so I'm putting another comma there. If we don't, then I'll just erase that comma. Right. Now it's like we just described, it starts bending up again, and it really has to, because we know we're bending up right here. So it's bending up, bending up, bending up, bending up. It's bending up until it starts to bend down again, because it starts to flatten out. And this one, you know, the way it's drawn, it's definitely not going to be concave up the whole time. And it's somewhere between 4 and 5. I would just guess around right here. So this is where it's bending up. And then since it starts flattening out again, this is where it's bending down. Once again, just imagine making the shape with your hand. Your palm has to be facing down if you want to make that shape with your hand right in this section. And how do we really say where that ends? Well, let's say it starts at 3 because it's where the other one ends, and it goes to around 4.3 or so. X is 4.3. Just use your best judgment. If you put 4.2 and the right answer is 4.3, if you put 4.3 and the right answer is 4.4 or something, you can't really see that perfectly with your eyes, and there's nothing wrong with that. Right? And then it starts bending down. It's bending down, it's bending down, it's bending down. And it's bending down really while it's flat until it starts up here again. So this little section, once again, imagine making this shape with your hand. It's going to be bending up, that your palm's going to be facing upward. So this is where it's concave down. It starts at 4.3 because it's where the other one ends. So wherever we said that, and it goes to about here. Maybe that's like 4.7. Yeah, somewhere between 4 and 5, and we can't really specify too specifically. But then after that, it's just bending up until we get to 5. It's going to be concave up the rest of the way. So from 4.5 all the way to 5. Now, one thing I want to definitely mention before, you know, we complete this problem or go on to the next step is that concavity, the idea is mainly to get a general picture in your head of what it looks like. What does it look like when a graph is concave up? What does it look like when a graph is concave down? It's that bending action. To me, this was always one of the hardest things to learn about Calculus 1 is it's much easier to see when a graph is going up or down, increasing or decreasing. It's a lot harder to tell what the concavity is. But you just want to have a general idea. You know, concavity, bending up, concave down, bending down, and so on. Okay. All right, but one nice thing about graphs is that if you've done this, you'll notice that our breaking points here, as far as local maximums and minima, which is the local extrema, are pretty much done for you. Why? Well, what's happening when it switches from increasing to decreasing here? We should recognize that this is a local max. It's at the top of a hill, so it's a local maximum, which is pretty much the way we could define it. Basically, it's everything around it has a lower y value. It's below it. So this is a local max. And we want the coordinates here. So I'll go ahead and specify this is a local max, even though we're only asked for the local extrema, just to label it. The x value is 2, and the y value, it's around 4. Maybe it's exactly 4. Maybe it's like 4.1. I'm just going to put 4 because it looks really close. But once again, on a graph, it's not necessarily easy to tell unless if you have those grid marks which intersect it perfectly. All right, now what else? Where do we have any more local maxes? Well, one thing is that we do not, because local maximums are going to happen when you go from increasing to decreasing. It's always going to happen like that. And we never go from increasing to decreasing again. But we do have the opposite. Actually, I'll use the same color here. We do go from decreasing to increasing down here. And you'll notice that this is a local min. It is the bottom of a hill right there. And that's always going to happen for a graph for at a local min, is you're going to go from decreasing to increasing. Once again, keep in mind that when I say going from one thing to another, it's red left to right. So local max is from increasing to decreasing. A local min is always going to be from decreasing to increasing. And the coordinates here, x is 4 and y, it's a little above 1. I could have drawn it in a way that maybe when I came across it, that looks like it's exactly 1, but I'm just going to put like 1.1. Once again, just you have to use your best judgment here. If it's exactly at the number, then put that number. If it's not exactly at the number, put it around there. So for me, I thought that the y value was a little above 1, so I'm putting it at 1.1. The x value is 4. All right, now points of inflection I haven't defined yet, but it's actually a little bit easier than even local extrema because we don't care for maximum minimum. We care about whether it's actually a maximum or minimum. But for points of inflection are where concavity changes sign. But it doesn't matter if it goes from plus to minus, so whether the second derivative is positive, negative, or minus to plus. As long as f prime prime of x changes sign at that point, and based on our graph, that just means if we go from concave up to concave down or concave down to concave up, that is a point of inflection. So I'll start by labeling all of them. And I really labeled everything about the second derivative above in this green and goldish color. So everywhere it switches color here, like right here, this is a point of inflection. I'll abbreviate it POI. And the coordinates there, it's about at x equals 1 and y is 3. So 1, 3. Now, do we have more? Yes, actually we have a couple more, right? Because we're concave down, but then it switches to concave up around right here. And that's happening around x equals 3. And the y value, it looks somewhere between 2 and 3, so maybe around 2.5, 2.6. Once again, you just got to use your best judgment here because it's not exactly on a number. So we'll do x was 3, and then the y value was around 2.6. And does it switch from concave up to down or the other way again? Yeah, it actually does it 2 more times. It does it again right here. Let me go ahead and label that as point of inflection. Point of inflection. And then another point of inflection. So one thing that's kind of interesting about this graph is it has 4 points of inflection, but only 2 extrema, a local max and a local min. And that's okay. You can have, they don't have to be related in numbers at all, just so you're aware of that. All right, so we did the first 2, the coordinates of this one here. The x value we used where this was breaking was 4.3. So I'm going to use 4.3 again, and then the y value, it looks like it's right around 2, so I'm going to use 2. And I only know I used 4.3 because I remember we ended the concave up at 4.3 and started the concave down at 4.3. So x is 4.3, and the y value we just figured out around 2 for this point of inflection. And then finally for this one, this x value we used was 4.7. So I'm going to match that where we had the last concave down ending and the last concave up starting was 4.7. And the y value here, it looks like it's pretty much in line with this one, which we used as 2.6. So x is 4.7 and y is 2.6. And these are all coordinates of points of inflection. One thing that's necessary when we're talking about a formula is that if your second derivative changes signs, that means the points of inflection have f prime prime of x equals 0. Because if it goes from positive to negative or negative to positive, it's got to be 0 in between there with some minor exceptions. But we're not going to worry about those minor exceptions right now because those are very rare and complicated examples. Okay. So one thing that you can kind of use points of inflection for if you get really comfortable reading the graphs is that they are spots where it goes from bending up to bending down or bending down to bending up. And it can be really helpful because it can tell you a lot of things. But we'll talk about those more specifically later on in the section about why the second derivative in concavity can be so useful. But for now, just try to get the idea of what's going on in your head down, because when we talk about doing these with just a formula, it'll make a lot more sense, because really what we're going to be doing is with a formula figuring out all these intervals anyway. But I'll see you in the next video.